Let's pick up where we left off in the previous topic. And in topic 2.1, we developed this expression. So we came up with this expression. We went back to that original question we had about how do we find the instantaneous rate of change of a function at a point, where we can look at a point on any function, not a linear function or not necessarily a linear function, but we could look at a point on that function and say, what is the rate of change at this exact instant? And then we learned limits all throughout Unit 1, and we kind of brought limits now to that table, and we said, okay, if we write this expression, the limit as h approaches 0 of f of a plus h minus f of a all over h, that would evaluate the instantaneous rate of change of a function at the value a. And so that's exactly what it does. It evaluates, not approximate, it actually evaluates the instantaneous rate of change of a function at a point. So we can ask ourselves now, okay, what is, and we did this with a linear example in the previous topic, but we can say, what is the instantaneous rate of change of the function f of x equal to x squared plus 3x minus 5 at the point x equals 3. So I've got this function, it's a quadratic, it's going to be in the shape of a parabola. I want to know what the instantaneous rate of change is at the value x equals 3. And what we did in topic 2.1 is we built the expression, the limit as h approaches 0. We're looking at x equals 3, so that's our value of a for this particular expression. So f of 3 plus h minus f of 3 all over h. And what we want to focus on now today is how do we evaluate this particular expression. And so one of the things that's going to be really nice for us to be able to do is if we can do a little bit of bookkeeping. And so I'm going to do our bookkeeping in red because I need to know what f of 3 plus h is. And rather than try to substitute it all into this expression, let's just figure out what it is off to the side. So I want to know what is the function value at 3 plus h, because then I can substitute it in right here. Well, that means to substitute 3 plus h into every value of x in this function. So it's 3 plus h quantity squared plus 3 times 3 plus h minus 5. All right, so what that equals, if I remember how to square a binomial, that ends up being 9 plus, I'll end up with 3 times h twice, so that's going to be 6h plus h squared. So there's 3 plus h quantity squared. Here I need to distribute the 3, so this is going to be plus 9 plus 3h, and then I still have that minus 5 trailing there. Now if I look, I can do a little bit of simplification here. I've got a single h squared. Let me slide my paper here so that I can get all of this. I've got a single h squared. If I look, I've got 6h and 3h, which is going to be 9h. And then my numeric values, I've got 9 and 9 minus 5. That's 18 minus 5, which is 13. So if I substitute 3 plus h into this quadratic, I get the return of h squared plus 9h plus 13. And you can see why I wanted to do this as part of my bookkeeping work off to the side, because it gets kind of messy. And this is only a quadratic. We're going to be able to do this with all types of functions. So I know what f of 3 plus h is. Let's look at f of 3, which is much easier to evaluate. F of 3 is going to be 3 squared plus 3 times 3 minus 5. Well, that's going to be 9 plus 9, which is 18, minus 5, which is 13. So now I know these values for f of 3 plus h and f of 3. So I can substitute them in, and let's see if we can evaluate this limit. So I've got the limit as h approaches 0 of f of 3 plus h, which we said was this right here, h squared plus 9h plus 13, minus f of 3, which was 13, all over h. Well, if I look at the numerator here, I've got plus 13 and I've got minus 13. So if I cancel those out, I can say this is the limit as h approaches 0 of h squared plus 9h over h. Now I can't use direct substitution yet because I can't substitute 0 into the denominator, but if I look, I can actually divide out an h from every term in the numerator. So this is now equal to the limit as h approaches 0. When I did h squared divided by h, I'm left with h, and 9h divided by h is 9. Now I've got the limit as h approaches 0 of h plus 9. Well, I can evaluate that with direct substitution. That means to substitute 0 in for my h. So this is 0 plus 9, which equals 9. And that's the value of the instantaneous rate of change. So if you were to graph this parabola and look at the point x equals 3, the instantaneous rate of change at that given point would be equal to 9. And we can actually evaluate it now that we know limits rather than building those big tedious tables that we did in topic 1.1. So we can get this answer by simply evaluating a limit. Now then the question is here, that was great to find it at x equals 3. But what if I wanted to know the rate of change of this function at x equals 0 or x equals negative 2? Well, it turns out I can actually write the rate of change of this function as a function itself. And that's what we're going to cover in the next video, which is actually a major topic when we look at the idea of calculus.